Welcome to Math260, Lesson 6. After that hard lesson on vector projection, scalar and vector projection, we're going to be back on something a little easier, an introduction to matrices. So, what is a matrix? Let's get a definition and then an example. A matrix is a rectangular array of numbers. In our case, real numbers. And the notation is typically with square brackets. I'll give you a simple example of a matrix: 3, 5, 7, 2, 4, 8, 6 minus 5, 3. This is a 3 by 3 matrix, a matrix with 3 rows and 3 columns. So typically matrices are labeled with capital letters, and I call that matrix A. And what they're good for is storing related sets of information. In fact, one way of thinking about matrices, an important way, is we can think of it as a collection of vectors. The vector with elements 3, 2, 6, another vector with elements 5, 4, negative 5, and another vector with elements 7, 8, and 3. And in fact, we can think of vectors in general. The vector v that we've been writing with angle brackets, 2, 6, minus 4, let's say, can also be thought of as a matrix with only one column. Like that. So we would say this is a 3 by 3 matrix because it has 3 rows and 3 columns. And this would be a 3 by 1 matrix because it has 3 rows and only 1 column. Now we'll also see later that we may also want to consider the rows of a matrix to be vectors. That is, we might consider this matrix as the first row is vector, the second row is another vector, the third row is another vector. But they have many more uses other than collecting vectors. Let's look at another example. A very common kind of matrix represents a table. So there's 4 students. With 4 quiz grades. So the labels would be outside the matrix, but we could represent this as long as we knew what the elements of the matrix signified as a 4 by 4 matrix. Let's say 3.7, 2.8, 5.2, 6.1, 4.3, etc. We could fill this with the actual grades of these individuals. So this would be a 4 by 4 matrix, where the content is understood to mean each row corresponds to the grades for one person, and each column corresponds to a different test, or quiz in this case. Okay, so that's the idea of a matrix. Let's look at some technical details. Suppose that A is a n by m matrix. Matrices are, everything about matrices, it's always row first, then column, so n rows and m columns. And we use lowercase letters to indicate the elements of the matrix. A, I, J would be the single element in the ith row and the jth column. So for example, the dimensions of this matrix would be rows, columns. So it's 2 by 3, 2 rows and 3 columns. And A11 would be the element in the first row and first column. A21 would be the element in the second row, first column. And A12 would be in the first row, second column, etc. So this is how we index or pick off individual elements of a matrix. Now it turns out, just like we can operate on vectors, we can add vectors and we can multiply vectors by a scalar, we can also do this with matrices in a very similar way. But using this, when we use this notation, first thing we want to define is matrix addition. First thing, in order to add two matrices, they must be of the same dimensions. They must have the same number of rows and the same number of columns. So I can only add matrices that are exactly the same dimensions, but if I do that, then if the matrix C is formed by adding the two matrices, A plus B, then the element in position ij of the matrix C is simply the addition of the corresponding elements in the two matrices. Just like with vectors, I add corresponding elements. With matrices, I add corresponding elements. So for example, if A is, we'll use an easy case, a 2 by 2 matrix, B is that, then A plus B, the matrix A plus B, is formed by adding element by element. So the first element in the matrix at position 1, 1 is 2 plus 5. The element at position 1, 2 is 4 plus 3. The element at position 2, 1 is 8 plus negative 2. And the last element at position 2, 2 is 6 plus 1. So I simply add corresponding elements, just like I do with vectors. In fact, I could think of this as being two vector additions. The vector 2, 8 added to the vector 5 minus 2, that would give me the vector 7, 6. And the vector 4, 6 added to the vector 3, 1, which would give me the vector 7, 7. So because of this way of thinking about matrix addition as a bunch of vector additions, matrix addition inherits all the properties of vector addition. Now let's also look at scalar multiplication. It's just like vector scalar multiplication also. I'll call the scalar k times a. If if that's my matrix C, then Cij, the ij element of the matrix where I multiply the scalar or real number k times the matrix A, I just multiply every element by k. So, for example, that's my matrix A with columns 1, 2, 3, 4, 5, 6, 3, 2, 1, and I multiply it by 5. I simply multiply every element by 5. So 5, 10, 15, 20, 25, 30, and then multiplying the last column by 5, 15, 10, and 5. So that's how we multiply a matrix by a scalar. Again, I can think of this as multiplying the first column by the constant, that is, multiply the vector by the constant, multiply the second column by the constant, multiply the third column by the constant, and again, because I can think of this as a set of scalar multiplications on vectors, scalar times matrix is going to behave just like vector times matrix. And we'll make use of that in a future lesson. We'll be able to show, in fact, that with this definition of matrix addition and matrix scalar multiplication, that the set of all matrices of a fixed size also behaves like a vector space. But we'll leave that for later. We have one more simple definition to cover. The transpose of a matrix. Written this way, A with a T in the exponent means A transpose. If I make the new matrix C as the transpose of the matrix A, then Cij is A Ji. What does that do? It reverses the roles of row and columns. That is, the rows of C are the columns of A. So, for example, so the first row of A is 3 minus 4, 2. The second row of A is 5, 6 minus 4. This is a 2 by 3 matrix, 2 rows and 3 columns. Then A transpose interchanges the rows of rows and columns. So the first column of A transpose is the first row of A. And the second column of A transpose is the second row of A. So notice if I and j are the same, that is C11 is going to be the same as A11, C22 is going to be the same as A22, etc. So these elements along the diagonal didn't move, but everything else got swapped, right? So that's the idea of a transpose. And this will come in very handy when we look at matrix multiplication in detail in an upcoming lesson. So let's put this together with an example. That includes all three operations: addition, scalar multiplication, and transpose. So there's my matrix A, first row 2, 4, 6, second row 5, 3, 1. my matrix B. First column, 5, 7, 3. Second column, 6, 4, 2. So right away, because this matrix has dimensions 2 by 3, this one has dimensions 3 by 2, I can't add them. But I can do the following. Twice A plus 3B transpose. The transpose of B is going to have dimensions 2 by 3, so it can be added to A. Let's work this out. What's 2A look like? I simply double every entry. And what does 3B transpose look like? I'm going to multiply each column of B by 3, and those are going to be the rows of my answer. So the first row is going to be 3 times 5, then 3 times 7, and then 3 times 3. And then the second row of the answer is going to be 3 times the second column here. And so I'm transposing. So 3 times 6, and then 3 times 4, and then 3 times 2. So this is 2A, and that's 3 times B transpose. And now I do the addition in the usual way. Element by element, 4 plus 15 is 19. 8 plus 21 is 29. 12 plus 9 is 31, is 21. 10 plus 18 is 28. 6 plus 12 is 18. And 2 plus 6 is 8. So there we have a working example. We've used matrix multiplication by a scalar, matrix transposition, and the addition of two matrices. And that concludes our introduction to matrices.